Hello there, welcome back to Life Lessons from Math. As always, I'm your host Wesley, and today I want to start off a 4-part series basically giving you an introduction into the big ideas behind calculus. So we'll approach 4 different topics within it. What is a limit? What is a derivative? What is an antiderivative, or equivalently, what is an integral? And then what is a Taylor series? So we'll basically approach those 4 questions over the next 4 videos, and as I talk about them, if you have questions, as always, feel free to reach out. Let me know how I'm doing. Let me know as I'm doing these things if you'd like to see me do more examples, if you'd like to see a little bit more math involved, just so that you can understand, what's going on, or if you'd rather me focus just kind of on the big ideas of what's going on. Yeah, just let me know how I'm doing and everything else. So today, like I said, I want to start off with the first really important thing, which is the idea of a limit. Basically, a limit is a mathematical tool that forms the backbone behind most of modern real analysis. So real analysis is just one of the many branches within mathematics, and the limit is the fundamental building block of real analysis. So anything with like calculus or PDEs, you really need to understand a limit to understand the why, the big ideas behind how all of that subject matter works. So with that being said, what is a limit? Basically, a limit is something that allows us to understand what happens when we approach some problem or difficulty, and it allows us to understand that problem or difficulty in a safe manner. So for instance, imagine, you have some function, but that function might require you to divide by 0 at some point, and it's like, oh shoot, I can't divide by 0. Like, that's just one of the big rules in mathematics. We can't divide by 0. Well, a limit allows you to basically understand what happens when you get close to dividing by 0 without actually dividing by 0. And through that process of understanding what happens as you get closer and closer to dividing by 0, you understand the behavior of actually dividing by 0. You understand what happens in the end when you reach that difficulty, that problem. Or imagine infinity. Infinity is a really weird thing, and when I do the video on series, I'll show why infinity can be so weird. But because infinity is just such a strange concept for us to grasp as finite beings, limits are really the tool we need to understand what happens at infinity. So through these things called limits, we can understand, again, what happens when we approach some problem or difficulty, what really matters in the long run. Limits have a tendency to really just kind of focus on what matters and who cares about everything else? Let's just really hit home on what matters. How do things behave eventually? How do things behave in the long run? Which are important questions for modeling, If you have some model for the economy, what's the economy going to look like in the long run? That's something you might want to understand through a limit. Or if you have some model for how medicine impacts the body, you might want to understand the long-term side effects of that medicine through something like a limit. Does that make sense? I hope that makes sense. So that's the big idea of a limit, is it allows us to understand problems and difficulties, what really matters, and long-term behavior. So, cool. Okay, that's a bunch of fancy words, Wesley. How does it work? We have the big idea. Now, how does that actually work mathematically? Well, one of my fundamental axioms, one of my guiding principles within mathematics, is that most of mathematics can be understood as the answer to a question. So if you understand the question, then you can understand the answer. So for a limit, the question you really need to understand, or that a limit tries to answer, is what does the output do when the input approaches a certain value? Okay, so again, keep that in your mind. We're wanting to understand how does the output behave as the input behaves a certain way. Okay, with that being said, let's imagine we have some function, let's say y equals f of x. Remember, with functions, x represents your input, y represents your output. So we have some function in the xy plane, and we want to know, well, what happens when my input approaches a certain value? So pick your favorite number, and I'm going to call that number a. So just because it's our favorite number, I'm going to use red, one of my two favorite colors, the other one being blue, to represent our favorite number. So you pick your favorite number. We want to understand, well, what does the output of that number look like? So I'm going to call that output L. Basically, how a limit behaves is like, okay, I want to understand what happens at A, where there might not be some difficulty happening at A. But let's just pretend there's some problem that happens at your favorite number. It's like, oh no, my favorite number's in trouble. So basically what you're going to do is you're going to draw a box around your favorite number with some stuff to the left and some stuff to the right. And you're going to squeeze that box together. So again, it's the limit. Just to actually write down the notation we use, we're looking at the limit as x goes to a of f of x. So our x is approaching a. So our x values are squeezing in on a from the left and from the right. So we're squeezing that in. And then we want to understand, okay, as I squeeze my inputs together, what happens to my outputs? So I look at the output of one end of my box and I look at the output of the other end of my box. Well, as I squeeze these together, notice that my outputs also squeeze together. So my outputs are squeezing together to give me L, whatever L is. So as my inputs get close to A, my outputs get close to L. So I would say that my limit as x approaches A of my function is L. Does that make sense? And I'll walk through some specific examples in a second, but I really want to make sure that idea sticks of, hey, I'm getting my inputs close to here, what happens to my outputs? And the outputs may not go to a certain number. So, for instance, imagine something like this. So let's say we have some function like this. So we have like y equals g of x. Well, as I approach this problem, so let's say my problem occurs at 5. As I approach 5 from the left, my y value is different than when I approach 5 from the right. And so in this case, the limit wouldn't exist because I need it to go to the same number when I go from the left and from the right. Does that make sense? When you are approaching some number, it needs to go to the same thing. So in practice, sometimes it's helpful to define the limit just from the left or the limit just from the right, but I'm not going to get into all of that. Really, that's just to kind of show that the limit doesn't have to exist if the problem is bad enough. If the problem is bad enough, when you go from the left, it's not the same as from the right, which means it's like, oh shoot, there's some kind of mismatch going on, some level of miscommunication. Because it's like, oh, I'm here and you're here, and it's like, you whiff. So, I hope that makes sense. Okay, so that's at any finite number. So how does it behave at, let's say, positive infinity? Or you can also do it at negative infinity, but I prefer to work with positive infinity if I can. Okay, so now let's say we're looking at some function like this. Let's call this y equals f of x. And I want to know the limit as x goes to positive infinity. So basically I do a similar thing. I want my x values to get close to that value. So if I want my x values to get close to a, or close to infinity, I basically need to look at large x values and then basically increase them. What happens as my x values get bigger and bigger? Well, notice as my x values get bigger and bigger, this function gets closer to this red line. So again, let's call that L. So because as my x values get bigger, my y values get closer to this line, I call that limit, oh, I forgot to put an f of x. My bad. I call that limit L. Does that make sense? Again, because my x values get close to infinity, my y values get close to L, so that's what I call my limit. Okay, cool. I hope that makes sense. That's the big idea of how it works in general. Now let's look at some more specific examples. So earlier I said, hey, this helps us overcome difficulties like dividing by 0. So how does it help us overcome difficulties like dividing by 0? Well, imagine we're looking at something like the limit as x goes to 0 of 5 divided by x squared. So as my x values, as my input gets closer to 0, this gets closer to dividing by 0. You know, at 0, I would have 5 divided by 0 squared, which is 5 divided by 0. That's no bueno, because I can't divide by 0. So what the limit actually allows me to do is it allows me to understand how does it behave by getting close to dividing by 0 without actually dividing by 0. Basically, I toe the line. It's like, I know I'm not supposed to divide by 0, but I'm going to get really close to it. I'm going to step right up next to breaking the line, breaking the rule, without actually ever breaking the rule. So how would you do this? So if you want to, you can in your calculator actually compute this limit and see what's going on. So imagine we have 5 divided by like 0.1 squared. Well, that's kind of close to 0, but let's make it a little bit closer to 0. So we look at 5 divided by 0.001 squared. Well, those are positive numbers. We also need to approach 0 from the left, i.e. with negative numbers. Consequently, let's try something like this. You know, negative 0.0001 squared. I probably didn't say enough zeros, but that doesn't matter. And basically what you find as you divide by numbers that are closer and closer to 0, this quantity is going to get bigger and bigger. The closer you get to dividing by 0, the bigger this number gets. Consequently, because you're getting bigger and bigger, we call this limit infinity. Because, again, it just explodes. The number gets bigger and bigger, and we call that a mathematical explosion. We call that blow up in math, whenever anything goes to infinity. So, boom, it just becomes uncontrollable. It goes to infinity. Does that make sense? So we never actually divided by 0. We just got really stinking close to dividing by 0, and notice what happened. We noticed that it just kept getting bigger. Cool. So how does this extend to, limits at infinity? Well, imagine, let's say we have the limit as x goes to infinity of the same thing. Let's say 5 divided by x squared. Well, again, rather than dividing by smaller and smaller numbers, we would divide by bigger and bigger numbers. So something like 5 divided by 100 squared, 5 divided by 1,000,000 squared, etc. And what you notice as you divide by bigger and bigger numbers in your calculator is that this number gets closer and closer to 0. So we would call that limit 0. I'm using a calculator-based approach here just because that's easy. That's something tractable that you can get your hands on and actually watch it happen and be like, oh, you're right, as I'm getting bigger and bigger, I get to infinity. Or smaller and smaller, I go to 0. We can actually rigorously prove this, but that requires a lot of heavy-duty machinery. If you want to see all that super heavy-duty machinery, I'm fine introducing it and showing you guys how you would actually prove something like this beyond all reasonable doubt, but I think the calculator is evidence enough of how this is working. But, limits don't have to go to 0 or infinity. we might have something like the limit as x goes to, let's say, 4 of x minus 4 over square root of x minus 2. That might seem a little bit weird at the moment, but what happens if I plug in 4? What happens at 4? Again, I'm going to kind of put this in red because this isn't how it actually works, but if I actually just plug in 4, well, I would get 4 minus 4 on top, and then the square root of 4 is 2, so I would get 2 minus 2 on the bottom, so that's 0 over 0, and it's like, oh, that's really weird. If dividing by 0 was weird, 0 divided by 0 is even weirder. And this is what's known as an indeterminate form. Basically, in math, whenever you see something like this in a limit, this can give you any number you want. This could give you 0, infinity, negative infinity, and anything in between. Negative pi, a billion, anything. So you have to be a little bit smarter with how it behaves. But again, you can do that approach that I was telling you about earlier. Well, what happens if I plug in 4.1 in for x? Square root of 4.1 minus 2. Or, let's say 3.9999 minus 4 over square root of 3.999 minus 2. Again, you just allow the x values to get closer to this from both the right side and the left side. And what you would find is that this would go to 4, I believe. Yeah. So, the limit can just go to some number just by basically, again, using that same calculator approach or the more heavy-duty machinery. So, does that make sense? I hope that makes sense. The last thing I kind of want to, well, there are two more things I really want to show you about limits and how limits behave. Like I said earlier, limits at infinity really have a tendency to pick up what really matters and leave everything else in the dust. Consequently, let's imagine we have something like the limit as x goes to infinity of x squared plus 7 over x cubed minus, let's say, 16. Something like this. Again, if I just naively plug it in, x equals infinity in, I would get infinity divided by infinity. Well, just like 0 divided by 0, that's really weird and can give us literally anything. So we have to be a little bit smarter with how we approach this problem than just naively throwing it in there. And I won't get into exactly how this works, but basically, whenever you're going to infinity, does adding by 7 really matter at all? No. The adding by 7 is insignificant compared to infinity. And because that adding by 7 is insignificant when we are going to infinity, let's just ignore that. And similarly, when you subtract 16, that's insignificant compared to x cubed as x goes to infinity. So we can basically ignore that. Again, I'm doing a lot of hand-wavy magic. Don't look at the man behind the curtain. But the big idea is that compared to infinity, constants really don't matter. We really just care about the variables as they're growing. So the limit is just this, and then we can actually simplify this now. This is now a much easier form to deal with, and we can actually simplify it. Right, remember this is just the limit as x goes to infinity of x times x over x times x times x. So 2 of those x's cancels with those 2 x's, and we're left with the limit as x goes to infinity of 1 divided by x. And now that's something we can deal with. And you can actually do the same thing with the calculator that I said before. Just plug in like 100, a million, a bajillion, and you'll find that this goes to 0. Again, because we just ignored the constants. It's just like, those don't really matter, so let's throw them away. Let's just focus on the important stuff. Does that make sense? I hope that makes sense on how these limits are really working. Again, they're allowing us to understand weird behavior, like dividing by 0, dividing by infinity, 0 divided by 0, infinity divided by infinity. It allows us to understand these weird problems and difficulties and challenges, and it allows us to just really focus on what really matters, because again, the constants don't really matter when where the limit is concerned. Okay, last thing I want to talk about before we get into the time of encouragement is that limits allow us to add up a lot of numbers. So what I mean by that is, imagine I have like 1 plus 1/2. I can throw that into my calculator. That's 1.5, Or let's say I add a third to it. Again, that's something I can compute in my calculator. Or 1/4. And I want to just keep this pattern going. It's like, okay, I want to do 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, etc. I just keep wanting to add all these up. Well, I can't add up all the way to infinity. So what I would have to do is I'd have to use a limit to actually be able to add this up. And this is one of the hints that infinity is really weird, is that whenever I actually add up all this stuff by using a limit, what I find is that this stuff adds up to infinity. Even though I'm adding smaller and smaller things, eventually I'm adding like 1 over a billion. And 1 over a billion is basically 0. Even though I'm adding basically 0 in the long run, that stuff that's basically 0 when I add it all up still adds up to infinity. So that's really weird. It doesn't make any sense. Infinity's bizarre. So, with that being said, I hope you have a decent idea on what a limit is and how it works. And, over the next few videos, I'll be using limits sparingly, but I'll have to use them to provide mainly just intuition is why we need a limit. We really just need a limit for intuition on how things behave and how we define things. So, with that being said, what's the life lesson from all of this? What's the encouragement for today? Basically, I want to encourage you to think about what plays the role of a limit in your life. Something I've tried to emphasize over and over in this video is that a limit really helps us to face our problems and understand them in a safe way. So what does that in your life? What allows you to look at your problems and challenges and difficulties and not run away from them? It's not, and to be like, oh, that's dividing by 0. Let's run away in fear. No, let's actually try to understand what happens when we divide by 0. Or that's 0 over 0. That's really freaky. No, a limit's like, it's not that bad. Let's approach it and talk with it and sit down with it and see how it works. How does it behave? What does it mean? So I want to encourage you to try to find something in your life that allows you to do that, to have that conversation of like, okay, I see that problem and that difficulty and that's scary, but how can I approach it? How can I start dealing with it? How can I embrace it to some extent and try to overcome it? It's like, okay, 0 divided by 0, that's weird, but how can I overcome it? Well, I can see what happens when I get closer and closer to it and see if that actually turns into anything. Again, that's how the math worked, but my challenge and my encouragement is that you can extend that idea to your life. And then, again, a limit tries to really just focus on what matters in the long run. So what in your life allows you to focus on what really matters in the long run? And if you want, I could do a video sharing what those things look like in my life. What are things that help me focus on what matters in the long run? What matters to me in the long run? How do I overcome my difficulties and challenges? How do I have those conversations with myself? How do I overcome depression and anxiety and stress and the madness of life, you know? Because I have a lot of views and theories and beliefs about how all that works. And I don't want to necessarily cram all my beliefs down your throat, but my challenge is to think about that in your own life and get you curious about your own introspection and how you try to overcome challenges. So I know that was repetitive throughout a lot of this video, and I'm sure I said so a lot of times, but I'm working on it. And again, why was I repetitive? Really just to try to drill the idea home. You know, I tried to say it in a lot of different ways so that hopefully one of those ways eventually sunk in of like, oh, so that's what's going on here. So if you have comments, questions about how I approach this or anything, if you want to see more examples of how this works, more explanation, leave those in the percentage section, i.e. the comment section down below. Just feel free to reach out to me on Facebook or Twitter or email. I believe those links should be in the description down below as well. Hopefully over the next few weeks, as I start making more and more videos, I get more and more engaged on Facebook and Twitter and everything. And let me know what you would like me to post on Facebook and Twitter. Would you like me to post just like random puns or random bits of encouragement or anything like that that you would just enjoy following, just enjoy my perspective on and everything else? So yeah, I hope that makes sense. I hope you guys have a wonderful day. Last thing, I would like it if you could just, again, comment. I want to make this a dialogue if I can. But sharing and subscribing would be great too. And I know every YouTube video has this, so I'm not going to try to do this at the end of every video, but I wanted to do it in this video of just like, hey, sharing and subscribing would really help the channel grow. And who would you share this with? Well, anyone who's curious about what does math look like under the hood? What are the big ideas, the core components of math? How does it apply to our lives? What does math research look like? Eventually, I'll get into showing you what research in the field of mathematics looks like. So anyone who's interested in that type of things, feel free to share with them. I would love it if you do. With that being said, I hope you guys have a wonderful day, and I will catch you on the flip side. Bye.